let's talk about section 5.4, the fundamental theorem of calculus. Right? We discussed this idea in relationships to areas traveled and the integral of a velocity curve. But essentially, the fundamental theorem of calculus says that big F of x is equal to the integral that if big F of x is equal to the integral from a to x of f of t dt, then f prime of x meaning the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. Translation? The integral is an antiderivative.
Well, wouldn't that just be like a dot?
Well, based on what we did last time, the answer is yeah. Now, I've done a different lecture. And maybe we can do a little bit of that same lecture right now, where you end up seeing that this case ends up being true, and that the pattern of the integral function has a relationship to the original function of a derivative function.
There's a pretty extensive explanation of it on Wikipedia. I mean, is that accurate? Have you seen that?
I haven't looked at the Wikipedia explanation of the fundamental theorem of calculus. I don't know whether I could prove this to you more than I did when we talked about the relationship of velocity and distance traveled, that velocity position relationship. But let's just, if you got this down, it means a couple of things. One, if this is the f of x curve, I'm going to draw one real quickly. Let's say that's the curve f of x. This is 5, this is 10, this is 15. If I went over to here, and said, draw me the curve from 0 to x of f of t dt. F of t dt. What would you do? Well, when x is 0, what does that integral function look like? Looks like the integral from 0 to 0. What value gets outputted from that expression? What's that? 0. So 0, 0 is a point on this function's curve. Right? And let's say, what about when x is, let's say when x is 2. Now what does that say? The integral from 0 to 2 the integral from 0 to 2 is equivalent to the area of that red rectangle or red triangle. 2? 2. Okay, so when I'm at 2, I'm there. Okay, what about when I'm at 4? Which would be the area of that blue triangle. 8? Boy, I wish I would have put the graph further down. Okay. In fact, I'm going to have to do that because this is going to go even higher. Hold on. Let me put this curve all the way down there. Okay, at 2 we had 2, at 4 we had 8.
No, 4
Yeah, 4 we had 8. What about when we're at 5? No, 12 and a half. Okay, and that 12 and a half, because that's the area of this green triangle. Okay, now it gets tougher. What about at 7? What's the area of that weird shape at 7? Well, how's this idea? It's 12 and a half plus this trapezoid. 20 and a half? 1, 2, 3, 4, 5, 6, 7, and another 8. 20 and a half. So at 7, we're at 20 and a half. 5, 10, 15, 20 and a half. All right? Hey, how long am I going to keep on going up? Till 10. Then what's going to happen? There's going to be a horizontal asymptote. When I add this last triangle there of space, 1, 2, 3, plus another 4 and a half, 25. Okay, so when I get to 10, comma 25, which is right there, then something happens to the area signified by that. I end up having to do something like dealing with this red triangle there. What's that? And because that curve is now below the axis, that's quote unquote negative area. And then so at 12, so here I am at 12, and I'm no longer at 25. I'm going to have to have gone down by 2. And what we see here is that there was a maximum. There's a maximum in the height of this curve, which I'm going to call the big F curve. That maximum occurred when? When this curve was equal to 0 and changed from positive to negative. That sounds familiar. That sounds like the first derivative test. A local maximum occurred here because the derivative was equal to 0 and it changed from positive to negative. Meaning, what's the relationship between this curve and that curve? A derivative. That's the derivative of this. This is the derivative of that, or this is the antiderivative of that. So the fundamental theorem of calculus states that these integral functions have an antiderivative relationship with the function inside the integrand. But it also means that there's some problems that we now can do, and do quite simply. For example, I could ask, hey, I've got this integral function from negative pi to x of the cosine of t dt. Hey, there's an integral function, right? You give me different values of x, I put them in the integral notation, and I get a number back out. You give me a different value of x, I get a different value out. I can do this again and again and again, right? Fundamental theorem of calculus part 1 says, what happens when I take the derivative of this expression? And the answer is, it goes, and it becomes cosine of x.
Why x and not t?
Because this expression is a function of x. when you give me different values to plug into this expression, I'm plugging it into an x value. So it's a function of x. I'm not plugging it into t. I'm plugging it into that value there.
So
If you said negative, if you said, what's this expression at negative pi? I would say, oh, integral from negative pi to negative pi, it's 0. I didn't touch the t's at all. I only have been placing different numbers into that value. It is a function of x, so x is the value that we're replacing to calculate the value.
So when you have your expression in there, you can use x as your variable?
The only variable you can't use is x. X cannot do double duty in that sense. Right? And of course, it seems silly. In the book, they do this example. Plus. It's supposed to be a plus. Let's see if I write it right. And you see that, and so now, since we know the integrals are the antiderivative function, what happens when I take the derivative of the antiderivative function?
It's the function.
It's the function. It's the function that's in the integrand. And that's it. Except, now that you say, well, that's simple, that's like plug and chug, that's substitution. That's when they get you. That's when they throw the curveball.
There's curveballs.
There's what?
There's curveballs.
There's curveballs. Would you like to see the curveball versions of these same questions?
Sure.
You ready? Here we go. Curveball. Oh, and I'll say secant. Just because secant is so overlooked. How is this problem different?
X, you're going starting at x.
Oh, I did not mean to do that. I just broke my own rule. Is that better?
You're starting at x and going to 1 instead of starting at a number and going to a zero.
What's that?
Would that be negative secant?
It will be, but why? You're right, because the thing that's different is that I flipped the order of integration. So how do we make it look like a problem that we've already done?
Negative. And flip.
Oh. If we change the order of integration, bless you. If we change the order of integration, we can do that as long as we put a multiply by -1. And you know what? I think we even have a derivative rule that basically said that will allow me to pull that negative sign all the way out here. Now what? Oh, now we can substitute. And then we're done. There's your first basic curveball. But you know what? Not only do we have a curveball, we have a slider. Are you ready for the slider version of this? Can I? Is it okay with me throwing around baseball terms like that?
Hit me with your best shot.
Best shot. Okay. Right. The slider version of this. What is the derivative with respect to x of the integral from 0 to x squared of, let's say, e to the u squared du? No, I don't want to use u. I'll use t. Continue to use t. How is this one different?
Oh, because you're going next way.
Because I'm going to X squared. It's not plain old X anymore.
Would it just be 2?
What it is that we have to make this look like a problem we already know how to do. I use a magic word. What's the magic word? Let. I'm going to create a brand new variable. That brand new variable is going to be called u. I'm going to let u be x squared. And what do we get? The integral from 0 to u of e to the t squared dt. And I'm going to take the derivative of that with respect to x. This is now still a function of x. U is a function of x. What do we get when we take the derivative of this function? I get e to the u squared du dx. I get a chain rule. Isn't that what happens when we have a function inside of a function? We have a chain rule. The u is really x squared, so it's e to the x squared squared. And then my chain rule is, what is the derivative of u with respect to x? In that case, it's 2x. Or e x to the 4th times 2x. So,
You said 4th, or you wrote?
oh, I wrote 4. I said 4. There we go. How's that? I do that all the time. I don't know why specifically. So there's the variations and how we can answer those same questions. Beep. How about that? All right.
So you just watched the football.
No,
So-
that's just right.
Let's summarize. FTC Part 1. The derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. It's fundamental theorem of calculus, Part 1. The derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. And of course, wherever there's a Part 1,
Part 2.
there's a Part 2. Are you ready for fundamental theorem of calculus Part 2?
Yes.
All right, you've already seen it. This isn't Back to the Future. This is calculus.
We're summarizing stuff, right?
No, I was just saying, we have to do FTC Part 2 as well. But you've already seen it. I've already introduced it. The integral from a to b of f of x dx is equal to big F of a, or big F of b minus big F of a, where big F prime is equal to little f. Fundamental theorem of calculus Part 2. I have got the excitement quotient down to a bare minimum based on the number of sleepy people I see in my classroom. Yes.
So, when you did before, when you were doing the derivative of an integral, you had it say from pi to a variable.
Mm-hmm.
The reason, because of this, you actually had f of x minus f of a number, and then because that would be the derivative of a number, that's why it's just minus 0.
Right. Let me catch everyone else up. we had some integral from 0 to, well, from 0 to x of t dt. The antiderivative of t is 1/2 t squared last time I checked. Is that correct? All right. I'm sorry. What I really meant to write here is f of x, big F of x minus big F of 0. And big F in this case is 1/2 t squared. This is equal to 1/2 t squared, x squared. So it's equal to 1/2 x squared minus, oh, I really wish I would have put 8 here. Oh, I'm so glad that I did. Okay. Ryan's point is, what happens when I take the derivative of this?
Second part is 0.
This part, all that is a constant. It ends up going away. And what happens when I take the derivative of 1/2 x squared? The derivative with respect to x of 1/2 x squared goes back to x just like we knew it should. Just like the integrand of our original problem. Right? Now the only thing that I haven't done, and Aaron, seeing that you've gone through this once before, would be, there's a notation issue. When I do these problems for realsies, I don't write this big F notation crap. I'm doing this to bring home the point that we take an antiderivative and we evaluate that antiderivative at 2 spots. All right? When we do this for real, in the vast majority of our problems, it looks like this. Let me grab a sample problem. The integral from -1 to 3 of x cubed plus 1 dx. We want to know the area under that curve while x ranges from -1 to 3. When we do this kind of problem in our homework, this big F notation gets really, really irksome. So instead what we say is, you know what, I think I can just write the antiderivative out. The antiderivative of x cubed, see, I add 1 to the exponent, but I also have to divide by that number,
Plus C. Oh, well, plus X.
plus
X.
x.
Plus
Now I could put a plus c in there. I could, but I'm not going to. All right? Because when you have 2 of these antiderivatives, if you have a plus c here, you end up having a minus c on the other side, and they end up canceling out every single time. So when we do these kinds of things, we leave off the plus c. We're not writing the most general antiderivative. We're finding the area under a curve. All right? Now there's my antiderivative, but I still have to bring in the notion that I'm going to take this antiderivative at 2 locations. So the notation that we add is half of a square bracket, and we put the lower bound on the bottom of the square bracket and the upper bound at the top of the square bracket. And that means that we're going to take that antiderivative and we're going to evaluate the antiderivative at those 2 locations.
Oh, it's in the homework, solution manual.
And that's the problem. They write the solution manual not in the context of where you're at that moment, but way we tend to do things later on. Just like, I forget, they did something else about like the antiderivative in one of your problems, and you didn't know the antiderivative integral connection yet. So bad on them. Yeah,
Does it matter if we do a bracket in the front or not?
it doesn't. the tendency is not to do a frontward bracket. That's the tendency. Unless we've got a whole chain of them and we're mixing them together. But if you wrote this, you'd be okay. Maybe even +1 for style. So, from here, what do? We take this expression and we plug our 3 in. 1/4 times 3 to the 4th plus 3. So there's our f of b. And now we're going to subtract off this expression with the -1 in all those places. 1/4 times -1 to the 4th. My board is out of calibration. Plus a -1. And as we clean up that now purely numerical expression, we'll get the area under the curve. 3 to the 4th is 81, so this is 81 fourths plus 3. -1 to the 4th is just plain old 1/4, so this is -1/4, and this is minus a -1, this is a +1. This looks like 80 fourths plus 4. 80 fourths is what, 20? No. Yeah, 20. 20 plus 4, or 24. Did someone, none of you have your calculators out? I'm so surprised.
I do.
Oh, okay. Can you quickly do a finite integral and confirm? At least their estimate is around 24. Can we confirm that that answer is correct? By looking at the way the calculator estimates?
Yep.
Charlie says it's 24? Okay. And that's how we do that. So, a little bit different notation, but it's the same principle we talked about last time. Finding the antiderivative at that 2 locations. No, actually, I know it was broken on Friday because I tried to dry my hands on Friday. I came out with wet hands.
Oh.
Okay. Yep. And I think that's it. I think you're ready to do. You're ready to do some problems. Yep. Your homework. Your homework. In section 5.4 is 1 through. Oh, they're all so good. It's so hard to stop. Well, let's just stop at 39 odd. Now remember, a lot of those problems are like, find the derivative of this integral function. Which is either a substitution, or a substitution with a chain rule, or a flip and a substitution. The first 1 through 20 have those characteristics. So the first 10 problems are going to have aren't that bad. They really aren't. Someone have their hand up. Nicole. Oh, I hadn't announced the final exam thing, did I? I don't think we're going to have a final exam. Because we are behind schedule, and I need us to bowl forward.
How about
Okay. The makeup test is Wednesday, Thursday. Yeah, the quiz tomorrow is only through 5.3. That is correct. Yes. Oh, can you hear your private report? Let me turn off the recording and let them give you your private report.